Yeah, so today we're going to go into distributed graph library. It's too bad not a lot of people are here. So this is, I would say, 1/3 of all your muscle minimum into data science. So we will have, oh, I just started it. Okay. Yeah, so this will essentially allow you to do this other standard way of distributed computing, which is bulk synchronous parallel processing on graph structures. Right? So this was even before MapReduce came about. So this was also parts of it were also open sourced by Google, called pre-Go model. Okay, so let's just see. Yeah, so this is this pre-Go paper. Okay, so okay. So what you want to first do is, if you're already running a Spark cluster in the Community Edition that has Spark 2.2, then terminate it and start a new cluster with Spark 2.1 and Scala 2.11. Okay, because we want a specific version. So then what you want to do is, go to libraries, so you can go to shared and create a library. So, and then I would go here, coordinates, or just search in Spark packages in Maven Central. So then when you're here in Spark packages, just search for graph frame. Let's see. Packages, I think, should work. Yeah, there's maybe a tiny bug, like you may have to go to Maven and then search and then come back. Some tiny UI bug, I think. So anyway, you should be able to find this. And I'll kind of wait until everyone is here, because the second notebook for today is actually going to be turned into a homework problem. Okay, so this is kind of the first time I think you guys are going to load a library with very specific version dependencies.
CrapFrames?
Yeah. CrapFrames. So is everyone here? Have you seen this? So this says that so yeah, 2.1, Spark 2.1, Scala 2.11, 0.5.0. That's the latest. So we don't see Spark 2.2. This is why we have to start the cluster with Spark 2.1, not 2.2. Okay. So then you just hit select, and that will load the library. Okay. Yeah.
Could you show again?
Okay, so let's make sure we do this, because we will hopefully start doing other libraries as well. So let's go to shared. Okay, it's just a shared area. I put all my libraries here. So I'm going to go create library. Okay.
And what does shared mean in this case?
Oh, it's just you can put it. It's shared just means you can write there. It's a shared folder. In the event there are multiple users, if this becomes a professional version, then you can put it anywhere. You can just whatever, go to your home, and so it really doesn't matter. So you can also do import, or sorry, create library, Okay. So, and then now you have to search, right? So, so there are many ways, right? So you can upload a jar file. This is typically what you'll be doing when you run some really big project. You can also upload, you know, Python eggs or whatever, but we're going to go to Maven coordinates. So then let's see. Then it should open up the search box here, search Spark packages box. So if you go here and then search for CrapFrame, okay. So you will get this. So is everyone here? Is anyone not here? Okay, so then you just select this. So that'll load that, you know, so you can also memorize this coordinate or whatever, Spark package thing. Then you say create library, okay? Hit this button. So then it'll basically create this library, and you can decide whether you want to automatically attach or not. Okay. I'm going to cancel because because I already have this thing attached. So, but you would want to attach this, okay? Yeah. So, okay. So once you attach this, you will have. So, for example, I already attached the right version here. Oops, this is the. Sorry, the wrong version. This is the right version. So you've attached it. Okay. So the other dependent problem is when you start the cluster, because this is Spark 2.1, Scala 2.11, your cluster should be launched to that version, right? So if you just launch the default one, it won't be Spark 2.1, it will be 2.2, which won't work. Generally shouldn't work. Okay. So then you can upload the SDS resources. So let me playing this dangerously because so let me just import the latest file. So okay, it's getting bigger now. It's 2.8 MB. So one notebook is already over 1 MB. Okay, so let's go here.
Wait, to upload the library?
Yeah, so the library has to be created and attached to your cluster, and then you have to grab the latest archive file. Yeah. So earlier I was just talking to Mariama about the stuff that maybe Eva was also confused maybe yesterday is I split the data into training and test 80-20, and then I took the training later on to do my cross-validation, my threefold cross-validation, right? So yeah, so training included the validation. And there is a subtle thing there. When you're doing the training, say with k-fold cross-validation, you're losing part of the data during the actual training, right? But you are also possibly gaining the optimal hyperparameter in this process, right? So there is this trade-off. Okay, is everyone here on CrapFrames now?
To restart the cluster, I think.
Okay, yeah, so you want Spark 2.1, Scala 2.11 cluster, so just terminate.
Yeah, I think I have to restart after I made the library.
Oh, okay. Actually, you can just detach and attach the notebook, but yeah. Oh, you're in 2. I don't know, maybe it'll work. You can try and see if it works. Okay, so let me try. So, you know, if everything goes well, you should be able to import these things and, you know, just execute these 3 cells and make sure we're all on the same page. And this should just load. Okay. So there should be no errors in the first 3 cells.
This special
Yeah. Good. Yeah. Go to your cluster. Yeah. Yeah, that looks like 2.1. No, it looks like you're running the correct cluster, right? Isn't it Spark 2.1?
Yeah.
Yeah, 2.1, Scala 2.11. So, no, I think that's it. So you just have to go to the notebook now. And, yeah, that's right. You have to update that because that's the big.
From yesterday, because
Yeah.
yesterday.
Yeah, no, it's today.
Yeah.
Yeah, so I'll make sure everyone's on this page because oh no, okay, so that's later on. So I think I think you're good. Yeah, you just have to that yeah, that sounds good. This is error because you have to validate the cell first. You know the big one. Yeah. Class there. Okay. Yeah, and then it should work. And I'll reevaluate that stuff. Maybe it doesn't work. Just go and show code. Yeah, it's a class. It's a full blown S3 class. So you evaluate this. I should evaluate. Okay, now try help. Yeah.
Oh, perfect. Yeah.
You're all good? Yeah. Okay. Is everyone okay? Mm-hmm. Good. Okay, so this is, I think, going to be one of your powerful weapons, I think, right? Graph processing, top sequence graph processing. So here are various guides. So I think the main GraphX paper you want to read is here. So this is, I mean, you know, when I show these papers, you can read it if you want to understand it, but let's just kind of get our hands dirty, right? Because we are in a hurry. The same with gradient boosted regression trees and random forests. You know, you can understand it at a deeper level in your own time. So this is the third main component, because there's machine learning library, Spark SQL, GraphX, and then the other one is structured streaming, which we will do next week. So the plan is before the 7 weeks are done, you guys have sort of your hands dirty on all the major components of Spark so that you can start thinking seriously about the project over the break. Okay, so and we will actually visit a lot of these algorithms, PageRank, connected components, motif finding, and various things today. So GraphX is basically sitting on top of Spark, and currently GraphX is somewhat outdated. There is a replacement, a community replacement for it called CrapFrames, and that's what we'll be using. Right? But the ideas are basically the same. So what's the main idea is to be able to use the so-called graph parallel abstraction, where we can do so-called vertex programming, right? Where we tell each vertex to do something, and the thing it does is it will, you know, transmit some messages to its neighboring vertices and receive messages from its neighboring vertices, and then it has to do something with the message it receives, and usually update its own state, and then it'll retransmit another message after this update. So if everyone is doing this in parallel and in a synchronous way, you can now have states at each vertex evolve over time, right? That's the basic idea of this kind of you know, distributed computing with graphs. Of course, the point is the graphs are, you know, allowed to be so big that they won't fit into one machine. So we'll have to basically take a really large graph and somehow chop it up and put it into different machines, right? So we will do PageRank concretely here. Let's so let me see if there's a quick picture on. So in let me see. Oh yeah. So here is the partitioning strategy. So this is a vertex cut partitioning. So you would cut certain vertices and then partition the graph so that this cut vertex is shared between different machines, and then the other sort of neighborhood of a subgraph will be put into one machine, so that when they communicate with your neighbors, there is very little inter-machine communication. That's the high-level idea. Okay, so let's get back here. Yes. Yeah, of course. So Databricks has its own thing. I just briefly looked at it, and whatever I'm doing is still quite current. There's nothing broken. So you can go through this in more detail as well. They're using different example data sets than the one I'm using. Here is your you know, basic idea in a picture. So far we've been doing this sort of data parallel computation with SQL, data frames, and data sets where we have row objects. And then these things are abstracted through this resilient distributed data sets that allow fault-tolerant computing. Right? So if nodes fail, we can still finish our task because we keep these recipes. But here it's, you know, at least the abstraction is different. We have, you know, graph parallel computations, but the way everything is implemented still uses RDDs under the hood in GraphX. So GraphLab, I think, actually know the advisor, the guy in Jerusalem University, Hebrew University in Jerusalem, that did GraphLab. I think GraphLab is now bought by, I forgot, it's Apple maybe. So that's no more. So this is this is what I was saying. You can either do a vertex cut or an edge cut. In Spark, the basic partitioning algorithm is vertex cuts. So this subgraph will go into one machine, this will go to another machine, and this will go to another machine. And then this shared vertex will say how to find the other nodes. Okay, so so these graphs in general are property graphs, so you can have nodes and edges, which are basically defined by pairs of nodes. And these are directed edges, so the ordered pairs of nodes. And then you can have properties associated both with the nodes as well as with the edges. Okay, so let's quickly see concrete examples right away. So we got this from this community Spark package, CrapFrames, and here is a Databricks blog about CrapFrames. So this is a bit more, this is a lot better than using CrapFrames. Okay. So let's just import SQL and CrapFrames, the library we loaded. Now what I'm going to do is just create this simple baby example throughout, and I'm marching you right through the programming guide for CrapFrames. Okay, pretty much every single thing in the programming guide. So this is a network of relationships between people. So the nodes are people, and the relationship could be follows or friends or whatever. So what we're going to do first is create a vertex data frame for all the nodes or vertices, and then we'll create an edge data frame. Okay. So in the vertex data frame, you have a special column named ID, which gives you the unique IDs that usually belongs for the vertex ID. And then it can have other columns for properties of vertices. And then in the edge data frame, you have two special column names called SRC and DST for source and destination IDs of the vertices, right? And these have to match with the vertex. Okay, so both data frames can have arbitrary other columns for properties, and then you can do all kinds of SQL expressions on top of it. The sound? I think they're just pumping more air into the room. Yeah. Okay, so this is good. So here's a simple example. I'm going to have I'm going to create a data frame using this list, where each element of the list is a tuple: A, Alice, 34, B, Bob, 36, and so on. And so my ID, ID can be string here. And then for the edge, I just have to make a list with the whatever I choose as my IDs, so pairs of IDs, ordered pairs, and so this will essentially represent that A is a friend of B. B follows C, and so on. So you have two kinds of properties for the relationship. So I convert this to a data frame for the edges and for the vertex, and all I have to do is load it as a graph frame. Okay, so my mutable g, lowercase g, is a graph frame made of the vertex and the edges. So we have this really massive thing here. So if I show the code, okay, some D3 stuff. I've been using this from before. This is, so I'm going to hide the code, and I'm going to run the cell, and it should have compiled now. And so I can have my function working. This is just to visualize, okay? So now I'm importing a literal, so I can have a column of the same constants. So what I'm going to do is create an immutable called G capital E, where I take the edges of my graph frame G, where I select the source destination as DEST, and then I add this new column, which is just the literal of ones, a long integer 1, and I name that column count. Okay, so I'm just doing this processing just to feed it. This is just ignore this really. So I'm just doing this so that I can have some notion of counts for each edge. So there's a weight 1. And then I can just use this to visualize. Okay. So in the next notebook, which will essentially be assigned homework, there is a lot more nodes than this. So it'll be all of this airline delay data over the US. Okay, it's just a visualization. So again, we hard-coded this using lists and converted them into a data frame, but you can load this example directly from the Spark CrapFrames package in the examples. So it's just, I'm just calling it G0, and you know, for my D3 thing, I need a thing called clicks, because we're just basically modifying that wiki click stream example. Yeah. So D3 is this, what is it called? Document-driven, data-driven documents. It's a visualization thing, right? So we use this for the wiki click stream, remember? It's just to visualize quickly for graphs. Oh, it doesn't?
No.
Oh, really? So you guys evaluated this cell.
And you have to run that one, otherwise.
Yeah, the one the previous one.
You know, I mean, this is. So let's actually see. There's a lot going on, right? This is actually a full-blown package with its own class and objects, and so it's kind of hidden away. But I don't want you to understand that, but just to use it. Okay. Yeah, so you can hide a lot of code. Is everyone not able to run it? Right. Yeah, this is the same exact thing from the wiki click streams, right? Yeah, that's why I even haven't changed the inputs to the function, right? So I still call clicks. It's just edge. So anyway, it's just to visualize what we created. And then we have, this is just, instead of doing it by hand, we can just load that same exact data set from this pre-made example. Right? And now I'm just calling this D3 in one go. So I have to specify height and width of the framing box, and then this thing called clicks, which essentially is the edges, but it unfortunately expects the destination to be DEST. I didn't really want to change the package, so I left it like this. Okay, and it expects a weighted edges, so I just made a lit one for weights. So, and then this as D3.edge converts, that into a D3 edge thing, which is what you need to make this plot. So, later on, we'll modify this so that it's superimposed on a continent, on the North American continental map. So these edges are actually geolocated and they have meanings like airplane paths and things like this. Okay, so all right, basic graph and data frame queries. What should we do? Well, now you can just flex your SQL muscles. So all of that is now compatible because we're simply just playing with graph data frames. So we can, of course, ask simple things like what are the vertices, g.vertices, so that gives me just my data frame back, right? With my Alice is ID A, age 34, and Charlie is ID C with age 30, and so on. So, okay, so there's one guy who's 60, or girl, Gabby. Okay. And then I can also ask what are the vertices of the graph frame G0 that I just pulled out of this preloaded thing, and it should be identical. Okay. So same, I can ask what are the edges. So the edges are just source ID, destination ID, and some other column. In this case, we call it relationship. And now we can ask other elementary attributes about, or statistics about the graph, which is in degree. So in degrees basically is how many edges are coming in to a given vertex. So this vertex F has 1 in degree, E has 1 in degree, D has 1, and C has 2, and so on. Right? Only C and B have 2 in degrees, and others have 1 in degree. So that should be sensible. If we go back to our picture. So you can ask, oh, there are 3 here, right? 3 edges, but we're asking in degrees, so these are actually directed edges, right? So there are arrows associated with these edges, which I haven't drawn here. So yeah, so if you just look at the edges, it should already make sense, right? So let's see. C has 2 in degree, so let's see what's all coming into 2. B is going into C, F is going into C, and that's it. So that's why C has 2 in degree, right? Okay, same thing, out degree. So these are probably the most primitive statistics. They affect everything about the structure, right? So here, I think E has in degree 2, out degree 2. So that means there are 2 edges going away from E, where E is the source, to somewhere else, and so on. And you can also ask degrees, right? So this should correspond to our picture, right? So E has degrees, so this can be either in or out. You just count everything. So this should be what we saw in the picture. Okay, so now you can run queries directly on the vertices data frame. For example, we can find the age of the youngest person in the graph. So no big deal. I just am doing a group by and finding the minimum age. So, so this is just a global group by and minimum age. So that's the youngest person.
There's a group by here.
Because I need some kind of aggregation, right? So let's try this.
Just because of the data type. Yeah, it gives an error because the minimum doesn't work on.
Yeah, because yeah, good. So yeah, exactly. So we need to group by. Well, we can do this group by if you want. What is that called?
I mean, as it is now, it doesn't really
name,
do anything,
ID?
right? Just the type of the data that we're working on changes, right?
Yeah.
Otherwise, it doesn't really do anything.
Well, minimum is an aggregator, right? The aggregator needs a group by statement to decide what it's aggregating on. Right? So, right, you're finding the minimum of, say, a column. So you still need you need some kind of group by, right, before you can aggregate. Okay, so what do you think this will happen? What will happen to this? So now I group by ID and okay, so let's just see. So let me just see. So what is g dot vertices dot show? So you should have ID, name, and age, right? So I'm, this what was here before
Okay.
is going to do a global minimum, right?
Mhm.
And yeah, so I think that's what I want. In this case, I just want the minimum age. Right? So I mean, there's nothing really interesting to group by here. It's a small data set, right?
Could you do some sort of select?
Yeah, so you can do, yeah, I mean, you can select something, I mean, because everything is unique, right? What am I going to group by? So I have to, we'll see a very complicated example very quickly, next notebook. So if I have lots of identical IDs, then I can group by that specific, ID, because there are lots of, let's say, sorry, we have to have unique IDs. So if I have lots of identical names, so there's ID A is Alice and ID J is also Alice and so on, then I can do some more interesting group bys. This is just a global group by. Okay, so you can run queries on the edges data frame, right? So I can say I want to filter the relationships to be follow. So I'm only interested in how many edges are follow relationship. So this is, again, we're just mixing our SQL with CrapFrame. Now this gets interesting. So we can start looking at motifs. And so let's say we're interested in specific patterns of nodes and edges that we want to detect. So you can immediately think about applications in bioinformatics and population genetics, all sorts of things, right? Because you're into PopGen, right? So, I mean, there is this full-blown pedigree of the Florida scrub jay, for example, right? I don't know if those guys published yet. They have SNPs and, I don't know, 6x or 10x resolution of SNPs for this whole population. So you have information for, I don't know, several decades on what each bird is, what its name is, when it was born, what nesting site, where it was, who its parents were. So you have this full-blown thing. So you can ask simple things like, I'm interested in motifs of siblings, that had a migrant father or migrant mother. So those are all motif finding problems. So you can quickly run this and then get all the samples that maybe you want to set up some kind of disease mapping thing or whatever you want to do. Right? The same thing in Twitter, like you can immediately turn this into a problem where every node is a user ID and Edge may have like timestamps, and the Edge may even have the original tweet or what was the relationship of that particular status update and things like this. So you can start quickly looking at patterns like A retweets two guys, within 1 hour or something like this. And you can define a lot of these problems in this way. So here we're just starting simple things, search for a pair of vertices with edges in both direction between them. So we're interested in finding undirected or bidirected edges. So we kind of use this language. So we're interested in some node A going to some other node B, and we call this to be edge E1. And then we're interested in this same node B going to A back to A, and we call that edge E2. Right? So find all the comebacks, undirected edges. So you can go from A to B and back. So then it just says, here are my patterns. So I can go from A, node A, which is ID B, name Bob, age 36, this node, to this other node, Charlie, age 30, ID C, and this is the edge that connects A to B, right? Follow relationship. And then from back to E2, right? So E2 takes C back to B. So there's only two undirected or bidirected patterns, motifs in this little example. Right?
In other words, it is solvable to find all the relationships in the graph.
Well, yeah. So if you want further and say I'm only interested in bidirected motifs, right? Basically, two edges can get back and forth. and then I can filter further and say I'm only interested in these things that are friends. So then you can sort of filter against follow.
But then, in this case, you could modify this code and find like a third generation of followers or something.
Yeah, exactly. Yeah, so you can just, yeah, exactly. So yeah, I think there are some examples down the road. Oh, here it is. So I can say, so I take my motifs, which is just this thing. It's exactly what we're doing next. And then I'm saying, find me the second node whose age is greater than 30. Right? So so now we get C going to B relationship, and B Bob is 36, so we filter it, right? So we missed the first row from here, basically. We're just filtering because the second node, Charlie, is 30. We're not interested in him, so we're only interested in this second row. So you can play with motifs and filters, and yeah. I mean, in the bioinformatics case, you can say, I do this, I'm interested in all sibling relationships, maybe, okay, and maybe the same mother, so maternal, yeah. So siblings that share the same mother, and then you can say there is some marker, and I want to filter all of them that have marker for this disease or whatever, some phenotype, same type. Okay, here is search for all directed triangles or triplets of vertices. Now this can get very interesting. You can start recommending friends to people based on this. In fact, based on things like this. So here I'm going to say A, B, C are my edges, are my nodes, and A, B, B arrow C, C arrow A are my edges. And I can define it in this pattern. And I want to find triangles, A going to B, B going to C, and C coming back to A. And that's my motif 3. Okay, so Esther, David, and David, Alice, and yeah, and Alice back to Esther. Okay, so those are static motif finding. Okay, so now what gets very elegant and beautiful, I think, is stateful querying. So now you can start surfing through this graph, looking for not just motifs, but motifs that satisfy some stateful queries. Right? So here is our example. Suppose we wish to identify a chain of 4 vertices with some property defined by a sequence of functions. So we can say, here are my 4 vertices, A, B, C, D, going in a chain. I want to identify the subset of chains matching this particular complicated filter. So this filter will have an initial state on this path, and then we update the state based on various features of A, various properties of the vertex A. And then we can update the state based on the next vertex, its properties on the chain, and so on. And then the final state that we get out of this, if it meets some condition, then we say we want this chain with 4 nodes that satisfy my stateful query. So here's a sort of concrete example. So we try to identify a chain of 4 vertices such that at least 2 of the 3 edges are friend relationships. Okay. So the state is the current count of friend edges, and this is just out of the programming guide, right? So we say my motif is chain 4, so I have my g.find defined like this, A, B, B, C, C, B. And then I'm querying in the following way. I define a method for updating my state given the next element of the motif. So this is just a function. This Scala function is called SumFriends, and it has 2 arguments. it has the column called CNT for count, and another column which is relationship, okay, called relationship, and it returns a column back. And what it's going to do is when the relationship column is equal to friend, it simply increments the count column by 1. Okay. Otherwise, it leaves count alone. So it's just a friend incrementer. Now, the other thing we need is so you want to use the sequence operation to apply the method to sequence of elements in the motif. So when here we define this condition. So here's my sequence operation. So I take my sequence like this, with the pattern A, B, B, C, C, D. So these are my edges. And then I'm doing a fold left, right? This is a scala fold left. So I'm going to be doing a reduce by folding from the left. And what am I doing? I'm simply taking the count and the edges, and I apply the sum function with the count and the column of the edge for relationship. So I simply have my chain, and then I use my sequence operation to fold from the left and simply update my friend count. Okay, so when this, that's basically all I have, right? And then finally I put it all together and use my filter. So chain with 2 friends 2 simply takes chain 4, which is my motif, and it checks if the condition is greater than 2. A condition is simply our sequence operation here. So all this does is takes my motif, it's a chain of 4, and applies the condition by folding left and essentially counting the number of friends in the edges. And then if that's more than 2, it's it's satisfied. So now I'm done, right? Looking for motifs and doing stateful queries, live, fully distributed. Okay. And I think this is a rich enough pattern. I think this can be generalized quite a lot. Right. So here is here's a crazy idea, and I'll break for Fika. So can you think of a way to use stateful queries in social media networks to find perpetrators of hate speech online who are possibly worthy of an investigation by domain experts, right, like intelligence and security experts, for potential prosecution on charges of having incited another person to cause physical violence? This is a real problem right now. You can have bids to the European Commission to compete for software, and it's a real problem. And I'm not kidding when I say you already know enough syntax. You know a little bit of Twitter and a little bit of streaming API, you can start rolling things. I mean, it won't be production ready code or anything, but you can really do quite a lot with Twitter, right?
Can you be prosecuted for that?
No. So this is some kind of software you can try to present to, because the European Commission has asked for bids to fight hate speech online because there are some laws they want to uphold. Some EU constitution and some laws about fighting hate speech, basically. So
only online.
Yeah, online hate speech only. Yeah, there's some specific law, I forgot the number. And they don't have currently any way of, doing this, right? So one could build a tool. I mean, this is a concrete example of some kind of entrepreneurship. And I'm serious. If you just do some basic NLP and process like full-blown Twitter data, you don't need a lot of resources, a few $1,000s. You can start collecting tweets for a large part of, say, Sweden. And then you can, essentially ask, like, here are some people who, are known to be, promoters of certain ideologies, and there are these people who are known to be, getting upset and reacting to it. So it's actually a fairly straightforward stateful computation. And it's not like you're saying this algorithm will go and prosecute the people. It's just a tool that someone in the domain, like a security person, can use to speed up their investigations. I mean, I'll shut up now. just one thing, right?